Another concept related to waves that we're going to talk about right now is the Doppler effect. The Doppler effect is something you've probably perceived, perhaps not even really trying to. If you've ever listened to cop cars or ambulance or fire engine, and my drawing, of course, is not the best. But as they're driving down the road, their lights are flashing. If the siren is also going and you're listening to them pass, as they get closer to you, as they are approaching, you hear the pitch or frequency increase. It gets higher as it comes towards you. As they drive past and continue on, you hear the pitch or frequency get lower. This is an example of the Doppler effect, specifically for sound, because you're listening. It's the sound that you're hearing change. The Doppler effect applies to light as well, but our eyes are not sensitive enough to see that change. We need equipment to be able to analyze the light, to observe the Doppler effect for light. Ultimately, what's happening is the sound waves that are being emitted. We know sound is longitudinal, meaning the air molecules end up compressed in areas, and then there's the rarefacted areas where the compression is smaller, and then compressions, and these compressions are moving through the air. Longitudinal waves are not particularly easy to draw, so I am going to draw the sine type wave, where we get compressions, rarefactions, compressions, and rarefactions. And so I'm going to represent the sound with the sine type wave that would describe its motion. So the siren itself, if the cop car or ambulance, whatever it is that we're listening to, if it were just sitting at rest, it emits a specific frequency. That frequency sometimes changes. Like we hear it going woo, woo type thing. For our equation that I'm going to introduce, we will be using F naught, and we're just going to assume one constant frequency. This is the emitted frequency. We're assuming to be the same, that it's not a changing frequency in terms of time. Okay, this frequency that is emitted, it's representing these compressions and rarefactions in the air, which represents the sound wave. What happens is these waves are being emitted, but because the ambulance or cop car, whatever it is that's emitting this sound, because it is also moving, what happens as it continues to emit the sound, these compressions get moved closer to the next compressions. And that's true. So if I was to represent the sine wave that we would be, sine or cosine wave that we would be hearing, we would hear a wave that has a smaller frequency. Sorry, I just am drawing wavelength, not frequency. So we're observing a wave now that has a smaller wavelength, which means we hear a wave with a higher frequency. So what we are observing is being affected by the motion of that cop car or ambulance, whatever it is that's emitting the sound. As the car continues away from us, this way, it's emitting the wave, but because it's also moving to the right, these compression areas become farther apart as far as our observations are concerned. If the compressions are observed farther apart, that means a longer wavelength is observed, and we hear a lower frequency. This is all based off of the speed of the wave being wavelength times frequency. We're assuming the air to be uniform, same temperature, no net motion of the air itself, so that the speed of the wave is constant. That means if we're observing a different wavelength, we're also observing, and in turn with sound, hearing a different frequency. So towards us, those compressions get closer together because of the motion. Closer together means a smaller or shorter wavelength, which in turn means the frequency is higher that we observe, and vice versa for motion away. When you look at the test notes, there's 3 different equations describing the Doppler effect. I actually like to use just the third one. This is specifically for sound. The equation looks like this. So F plus minus represents what we hear. So what is heard because of the motion? Whoever the observer is, that F plus minus represents either the higher frequency or lower frequency that is heard because of the motion. That's what that plus minus means. We either hear something higher or a frequency that's lower simply because of this motion. This will equal F naught, the actual emitted frequency, times this quantity. And I will explain what these pieces mean. So V with no subscript is the speed of sound. That will depend upon the air temperature, but whatever the speed of sound is in this particular condition, that's what we use for V. V sub 0 is the speed of the observer. Write that better. Observer, the one listening, the one that is hearing the higher or lower frequency. And of course, the observer does not need to be moving. In the previous example where I was talking about we're standing there as the cop car goes by, what the speed of the observer in that case would be 0, which is fine. V sub S is the speed of the source. Now, in each situation, technically, these are the components that point directly towards us or away from us. So if the car is traveling down the road that we're not standing in the middle of, at any given moment in time, the velocity is going to have a component that points directly towards the observer and a component that's perpendicular. It's only the component that points directly to the observer that matters in this equation. As the car continues to move, the component that points directly towards us changes. And that's why we hear a continual change in pitch as the car approaches and then recedes. That component of the velocity that points either directly towards or away from you as the observer is what matters. As far as problems we're going to solve, we are going to assume all motion is along the same line. So somehow the car's driving directly towards us. We're standing in the middle of the road. So erase my big person here. Or it's driving directly away from us so that the velocities given are directly towards or away from us. Just to simplify the problems for us a bit. But please understand the components are what really matters. And because we don't stand in the middle of a road as the cop car is driving down the street, that's why we hear a continual change in frequency. Whereas if we were standing in the road, we would hear the whole time the cop car is approaching, we would hear the same higher frequency the whole time they were approaching, as long as they were driving at the same speed towards us. Realistically, we don't stand in the middle of the road, and thus we hear a change in pitch because of the change in the component of the velocity that points towards us. All right, so V in this equation, speed of sound, if we are not given a temperature, so we can't use the equation that we have that allows us to calculate for the speed of sound based off of temperature, then we're going to use the 343 meters per second that is also listed. So we're going to be assuming the 20 degrees Celsius, unless we're given a temperature. The speed of the observer, how fast the observer is going, and then speed of the source. It is totally possible one of those is 0, which is fine. If that's the case, the equation simplifies to one of the other two equations that are in the test notes. But you can use those in the first place if only the source or observer are moving. I like this equation because it fits every single problem, and I can put in 0 just fine if that happens to be the special case of my problem. Now, in terms of the signs, in the numerator, these signs are chosen, so we choose the signs, or the sign, either one of them, based off the observer, what the observer is doing. So V sub O is in the numerator. V sub O means the observer speed, so those top signs are based off of the observer. The positive sign is used if the observer moves in a direction that takes them towards the location of the source, regardless of whether the source is moving away or towards. Just if, for example, let's say we had the cop car traveling to the right, but we're in our own car traveling to the right. So V of the source would be the cop car, V sub O is us. Since we're moving in this situation away from the source, we would use the minus sign. So in the numerator, we use the minus sign if the observer moves away from source. So to the right, the source is not over here. And that's why we consider that away from the source. Towards the source, we would need to be driving to the left towards this location where the source is located. So the sign in the numerator is just based on what the observer themselves is doing. And of course, if the observer is not moving and we put in a 0, it doesn't matter if we add or subtract 0. So we only have to choose the sign if the observer themselves is moving. And it's based off of whether they're moving towards where the source is located or away from where the source is located. Similarly, the signs in the denominator, we choose this sign based off the source. What is the source doing? And we can remember that because we have V sub s down here. V sub s means the speed of the source. And so we only care about what the source is doing. Now, the reason the plus minus is drawn in the opposite order is so that this sign that is top. So out of these two signs right here, the top of them is negative. We choose this if the source moves towards the observer. In the numerator, we used positive if the observer moved towards the source. In the denominator, we choose the top of the two signs. In this case, it's negative. Negative if the source moves towards the observer. Positive if the source moves away from the observer. Now, we cannot use a relative velocity equation. What I mean is, so for example, let's say we have this cop car, and they're traveling at 45 meters per second. This would be our source. Let's say the frequency of the siren, which I have absolutely no idea the frequency of a cop car siren, so I'm just going to make up a number. 640 hertz. So the actual frequency emitted, 640 hertz. Let's say they're driving to the right. We're driving down the freeway, for example, and they're driving at 45 meters per second. We are driving at, well, let's go the speed limit. So 70 would be around 35. Let's be doing 35 meters per second. So they're not coming after us. But we happen to be they happen to be behind us, coming towards us. So since the cop car is going 45 while we are going 35, the cop car, of course, is approaching us. They're getting closer and closer. What frequency would we hear in the situation where they are still behind us? They have not passed us yet. So assuming they're directly behind us, a ways away, but headed directly towards us at the moment. Because they're going to be getting closer and closer to us, we would expect to hear a higher frequency. So any overall motion towards, we expect to hear something higher. So plugging numbers in, I would put my 640 hertz in for the F naught. I'm going to put 343 in for the speed of sound, because we haven't been told otherwise, a different temperature to work with. Oh, I've labeled these both as sources. Sorry, in the picture. This is us, the observer. So our speed as the observer goes in the numerator. The source's speed, the cop car, goes in the denominator. And then we need to choose the signs based off of, in the numerator, what the observer is doing. So in this exact situation right here, we are moving away from the source. So we would choose, oh dear, sorry about that. Don't know how I just made this a lot bigger. Didn't. Let's just do that. Since we are moving away from the source, we take the bottom of the two signs that are up there by V sub O. In the denominator, the source, this cop car, is moving towards us. Towards us, we would use the negative sign in the denominator. So plugging these values in, I'm getting 661 hertz. So in 2 sig figs, approximately 660 hertz. This is higher than the 640. We do hear higher. We get an exact value. We would hear that same higher pitch the whole time as long as this motion is all along the same line. Now, what I mean by we cannot use relative motion, assume V of the observer is 0, and then say the source, the difference here between the 35 and 45 is 10. So the source is essentially, from our perspective in our car, would be moving at 10 meters per second relative to us. We cannot use these values in the Doppler shifty equation and come up with the same frequency that we hear. We have to account for the source moving and the observer moving. If they both are, we have to account for them separately, which is what the equation does. And that's why I like this equation. It works for all situations. Only one of them moving, the other one not, or both of them moving. This equation fits every situation. If we had this cop car still traveling 45, but we were traveling the other direction at 35, and again, assuming we're along the same line, just to simplify the calculation, we'll also assume we don't ever crash. The setup would have been very similar because everyone's still traveling at the same speed. I'm still assuming sound travels at 343 under these same conditions. We are the observer. We're still traveling at 35 meters per second. The cop car is still traveling at 45. But the difference is, as the observer driving to the left, that's towards the source. So I would use a positive sign in the numerator. I would still use a negative sign in the denominator because the source is still moving towards the observer. So ultimately, we're just having to change the sign in the numerator because of that change in the direction we are traveling in as the observer. So plugging these numbers in, I'm getting 811.8, so roughly 810 hertz. That's a lot bigger than what we heard when we were traveling in the opposite direction. But hopefully that makes sense. We're coming closer and closer and closer to that cop car very quickly in this case. So Doppler effect for sound is we hear a higher or lower frequency based off of motion. So motion towards, we hear a frequency higher than what's actually being emitted. Motion away, we hear a lower frequency. So sound, that is that previous equation. Light also, light will also demonstrate the Doppler effect. We cannot observe it with just our eyeballs. Our eyes are not sensitive enough to see that. But if we have what's called a spectrometer, which spreads all the different wavelengths across a larger space, we call it a spectrum. So for example, if I was to shine a regular incandescent light bulb that emits all wavelengths of light, I would see an entire rainbow spread over a large line. a spectrometer is able to essentially spread out this rainbow. Similar to a prism, but even better. When we look at stars, for example, we see this spectrum, but then we'll see, depending upon what we're looking at, some lines. So we'll see some black lines, and these black lines correspond to the elements like hydrogen that is in the gases of this star, that it's absorbing some of this energy. If a star that is being observed happens to be moving towards or away from the observer, so us on Earth, for example, if it's moving towards us, someone that is collecting this light that would be expecting these black lines end up seeing that they're shifted to the right. We call this a blue shift. This would be for motion towards, also referred to as approaching. So similar to sound, the sound wave that's traveling towards us, if the source is also moving, that puts the compression points closer together, meaning a smaller wavelength, and thus we hear a higher frequency. Conceptually, it's very similar. Motion towards us, that light we observe the wavelengths to be shorter. Now, not that you should expect to know this, but the red end of the visible spectrum is the longest wavelength out of visible light. Out of visible light, violet is the shortest wavelength. And so if we see a shift of an expected wavelength to the right, like this, we call that the blue shift, and we can get an idea of how fast that star is moving, or whatever it is we're looking at. Similarly, if there's motion away, to represent our rainbow again, that original dotted line would be over to the left. It'd be closer to the red end, meaning we are observing a longer wavelength. We call this a red shift. This is for motion away, which is also called receding. And so when we talk about red shifted light or blue shifted light, this would be in the field of astronomy that we're looking at that. We can get an idea of the component of the motion of the star or whatever it is we're looking at how fast it is traveling. So our equation we have, let me try that again. The wavelength that we observe, the observed wavelength, the subscript of red and blue means we are either observing a red shift or a blue shift. This is going to equal the actual wavelength that we're expecting because of expecting the star to be made of hydrogen. That hydrogen absorbs or emits very specific wavelengths times the square root plus or minus v of the source over the speed of light divided by 1 minus or plus v of the source over the speed of light. And the signs similarly are, in this case, going to depend just on the source. We're treating our motion as zero in that astronomical sense. And for example, if we measure what we observed and know what wavelength we're expecting, because we know the specific wavelengths hydrogen gases absorb or emit, we can work backwards and find v sub s, the source's speed. Similar with the sound, that will only be the component of the velocity, the source's velocity directly towards or away from us. But that's still some good information to work with. They give us the equation for frequency as well. It's very similar. But in the field of astronomy, I believe they work with wavelengths more than frequency, though they're certainly related because we know the speed of light is wavelength times frequency. So Doppler effect means we're observing. So if it's light, we would see a different wavelength. With sound, we hear a different frequency because of any motion directly towards or away between the source and the observer. That's what we're talking about with the Doppler effect.